All right, in this module, we're going to talk about how to classify igneous rocks, both volcanic and plutonic. Talk about some textual terms that we use to distinguish between the two. Discuss the compositional range of igneous rocks, what the color index is and how it can be used to estimate the composition of the rock. I'll show you the IUGS diagrams that are used to name plutonic rocks and how to read a ternary plot. And then we'll talk a little bit more about Bowen's reaction series. Okay, so the textual terms to get us started are these three terms: phaneritic. And the phaneritic term is used to describe a plutonic rock, but an igneous rock that has crystals that are visible with the naked eye. Okay, so we only ever use phaneritic to describe plutonic, or we can also call them intrusive rocks. Now, volcanic rocks have two other terms that broadly describe extrusive rocks. And an aphanitic texture is a texture in which the crystals are too small to see with the naked eye. You would need a thin section to actually see the minerals in the rock. And that applies to volcanic or extrusive rocks only. The other term that's only for volcanic rocks is porphyritic. And we use porphyritic when there are two different grain sizes. There are large crystals that are visible that are called phenocrysts, and there are also small crystals in the matrix of the rock, or we call it the ground mass. And so the ground mass itself has an aphanitic texture, but there are large phenocrysts in it, and so we give the overall texture of a rock like that the name porphyritic. All right, when it comes to igneous rocks, we broadly classify them based on chemical composition and on the texture. And so you'll see here that I've got rocks side by side. Up at top here, we've got the two texturally different rocks, but compositionally they're the same. Those are an example of a granite there and a rhyolite there. It's also possible to have a glassy texture, as in this obsidian that's off to the right. So we're looking at, in the granite, porphyritic texture, in the rhyolite, an aphanitic texture, and then a glassy texture if we've got a rhyolitic obsidian. Now, so all three of those rocks at the top have the same chemical composition, even though they look quite different. They just have different textures. So the granite was cooled and crystallized deep below Earth's surface, and so the crystals had a long time to grow. The rhyolite was erupted onto the surface, and the crystals cooled much more quickly and didn't have time to grow very large, and the glass was quenched so rapidly that it's not crystalline at all. There are no minerals in it. It is just a glass that has an overall chemical composition, same as the rhyolite and the granite. Then let's look down at the bottom there, where we've got a plutonic and a volcanic equivalent of a basalt. Let's change our pen color here so you can see. The basalt on the right, the volcanic equivalent to the plutonic gabbro on the left. It's a little bit hard to see in this image that the texture is different, but if you had this in front of you, you would see that there were large crystals visible in the gabbro, versus in the basalt you couldn't see very much at all. And in between, we have a chemistry of those two rocks in the middle that is somewhere between the granite and the rhyolite and the basalt and the gabbro. And we can call those two a diorite and an andesite. So I've described these rock names to you, explained that the rocks on the left are plutonic rocks, the rocks on the right are volcanic rocks. We've got obsidian over there. It's also volcanic texture and the glassy texture. Now, there are two terms that you need to learn at this point, and those are felsic and mafic. And felsic and mafic are generic terms to describe the chemistry of an igneous rock. And felsic derives its name from fel for feldspar, spar there, and silica, Si. So the felsic rocks are much more rich in feldspar and silica and are generally lighter colored. Mafic rocks down at the bottom you see are darker colored, and that results from more magnesium, so mafic from magnesium, and iron, Fe. So those mafic rocks have much more iron and magnesium and less feldspar and silica in them. Now, I'm also using the term silica. I'm not really saying I am saying silicon, but I'm using the term silica to mean a silicate that contains silicate minerals, or that has a lot of silicon in the overall chemistry of the rocks. And because the vast majority of the minerals in these rocks are silicates, that's what I'm talking about. It's not just quartz that I'm talking about. That is specifically SiO2. That's not what I mean. I mean just the silicon and oxygen at the end of those mineral formulae. So I hope I've made it clear that these textural differences, let's just use the andesite and this is a quartz monzonite in this example, but that those two rocks, even though they have a very different texture, have the same chemistry. So that if you were to crush them up, grind them up into a powder, and analyze them with some kind of instrument, let's say by X-ray fluorescence, you would see that they have the exact same amount of silicon, oxygen, magnesium, iron, sodium, potassium, etc. Okay. Those terms, felsic, intermediate, mafic, we also have an ultramafic rock, which has even more of the mafic minerals and less silica. But those are generic ways that we can classify igneous rocks. And I've just explained that the felsic term comes from the fact that it contains feldspar and silica. We're talking broadly, it's about 55 to 70% silica. That's the silicon and oxygen at the end of those mineral formulae. K feldspar is a dominant feldspar, so it's going to comprise about a third of the feldspars that are present on the rock. And these rocks are generally light colored and are found in the continental crust. Next we've got intermediate. Let's go down to mafic. We've got mafic rocks, when I explained that that's from the magnesium and the iron that is more abundant in the mafic rocks. That has less silica in it, so that's more like 45 to 50% silica. And there we've got the calcium-rich plagioclases like anorthite that dominate over all the feldspar in that rock. And so that kind of leaves us with the intermediate rocks somewhere in between, where we've got 55 to 65% silica. Plagioclase is more abundant than the K spars in intermediate rocks. But in the intermediate rocks, it's the sodium-rich plagioclase that dominates over the calcium-rich plagioclase. All right, and then finally, ultramafic rocks. And these are rocks that are found in the mantle. In that case, we've got over 90% mafic minerals in those rocks, and silica comprises less than 45%. And there may be no feldspars whatsoever. Instead, it's pyroxenes and olivines. Okay. We've talked about these terms, so I've got the composition here, felsic, intermediate, mafic, ultramafic, for generic chemistries of the rocks. Some names of phaneritic, examples. So, sorry guys, trying to get used to this software to annotate. The phaneritic rock names for the plutonic equivalents of those different chemistries, then the aphanitic or volcanic rocks that will be equivalent to those phaneritic textures. And then something that's called the color index. And that is the percentage of dark minerals in the rock. And, color is misleading, but it can help with igneous rocks. And just kind of getting an idea broadly, are we looking at a felsic, intermediate, or mafic rock, or ultramafic rock? And so you can see that felsic rocks maybe have 10 to 20% dark minerals, and those minerals could be biotite, pyroxene, hornblende, olivine. Those are the dark minerals that I'm talking about. So relatively few percent of dark minerals. Mafic rocks might be as much as 50% mafic minerals, and the rest would be plagioclase, mostly. And then ultramafic rocks, 95% of the minerals in an ultramafic rock are going to be dark minerals. Now, this works pretty well. It's particularly helpful for plutonic rocks where you can see the different crystals. It can be misleading. For instance, if you have a dunite, which is which is mostly olivine. I'll just abbreviate that, olivine, OL. It's going to look green, so it's not really the black pyroxenes or hornblendes or biotites. So that can be misleading in that respect. But otherwise, you kind of see where I'm going with this. Now, it's a little bit trickier with the volcanic rocks. Basalts generally are black, but they can weather to red colors. Andesites are often darker than rhyolites, but again, that's variable. So I'm going to show you when we get to the volcanic rocks how to use the phenocrysts that you can see, or what you can see in terms of the birefringence when you're looking at a thin section of the ground mass minerals to try to differentiate felsic from intermediate and mafic rocks. All right. Now, I just explained that percentages of the dark minerals can be used to estimate the composition. And I just want to point out, this is a resource that's separately available on iLearn. But here's an example of finer grained, here we go again, I gotta get used to this, finer grained minerals it's a plutonic rock, for example, where you can actually see the crystals, but they're smaller than these crystals down here. These are equivalent, so these two examples show 20% dark minerals. These two examples over here show 50% dark minerals. And I just want you to have some kind of guide as you're looking at plutonic rocks to start, what 50% dark minerals looks like, what 20% looks like, what 10% or 1% looks like. And I want you to use that sheet to help you, because your eye definitely overestimates the percentage of dark minerals in rocks. All right, so plutonic rocks specifically, we use these IUGS diagrams to name the rocks. And so you'll see rock names that you recognize, like granite, maybe granodiorite. Over here you see some diorite, gabbro. These diagrams and those rock names for plutonic rocks, and this is for felsic and intermediate only. So this is felsic and intermediate only. I'll get to the mafic and ultramafic next. But you name those rocks only using quartz. That's what the Q up the top of that diagram is. The P is for plagioclase, and the A is for the alkali feldspars. You're only using the K-spars, the quartz, and the plagioclase to name those rocks. You disregard completely any biotite, any muscovite, any hornblende, pyroxene. You don't consider those minerals at all, or anything else that's in the rock. You're naming it solely on those minerals. And we'll work at an example in class on how to read this more carefully and how to use just the quartz, K-spar, and plagioclase. All right, those diagrams are, this is how they're organized. We just look at the example of the, I'll call it, from now on, I'll call it the QAP IUGS diagram. In that last example, we had quartz up here. Let me change the pen color so you can see it better. Quartz up here, plage down here, alkali feldspars there. And what this diagram shows you is that in the quartz, if your rock would plot up at the top of the diagram here, because you're telling me it has 100% quartz, you would name your rock whatever is appropriate from that IUGS diagram right up there. If your rock had 100% plagioclase, it would plot in that corner. 100% K feldspar would plot in that corner. This line down at the bottom, therefore, represents a mixture between alkali feldspar and plagioclase, but 0% quartz. So 100% quartz up here, 0% quartz on that line. Same for the alkali feldspar. 100% on this side, 0 on this side, on that line. And so these dotted lines in here represent 10, 20, 30, 40, 50, 60, 70, 80, 90, 100% alkali feldspar. That's how you read this diagram. So in any given direction, you're reading the diagram the same way to whatever corner of the ternary diagram you're approaching. Now, this is showing us a chemistry for a rock that is different color, but a rock that is 70% quartz, 20% plage, and 10% K-spar. I'll just use A. How you would take these percentages and then plot it on this diagram will work like this. If you have 10% A, there's A, this line is 0%. So the 10% line is this one, 10% alkali feldspar. 20% plagioclase would be, here's 0 plagioclase, 10, 20% plagioclase. And then 70% quartz. So 10, 20, 30, 40, 50, 60, 70% quartz. And what you end up with is, let's see, what you end up with is the name of the rock corresponding to that spot on the ternary diagram. So if we were to go to back to that the IUGS diagram, that spot was somewhere up here, wasn't it? It was 70%. It was, oops. It was, let me get my pen. It was right about there, something like that. So those percentages led us to call this rock a quartz-rich granitoid. It's fairly rare. But I want you to be able to do that yourself, and I'll explain how to go from looking at a rock that's comprised of many more minerals than just quartz, alkali feldspar, and plagioclase to get to those percentages and then use this diagram. All right, you may have noticed that there is this other half of the diagram down here, and we're basically hardly ever going to use it or talk about it. But what that side of the diagram is, and you'll notice the F down at the bottom, are for feldspathoids. They are not feldspars, they are feldspathoids, and those minerals only grow when you have a rock, the bulk composition has too little silica to crystallize feldspars, and those are relatively rare. So we don't end up plotting down in that part of the IUGS diagram, at least with the rocks in our lab, very often, if ever. You'll see the feldspathoids show up on your mineral formula list. So we will look at some and consider some, but rarely will we use that end of the diagram. Okay. Now, these two diagrams work exactly the same way, but the one in the upper left is labeled gabbroic rocks. This is from mafic rocks only. Mafic rocks only, and the one in the lower right is ultramafic rocks only. And they differ, of course, in where the fields lie in the different rock names, what the different rock names are. But the mafic classification diagram, look at the corners of the diagram. You see plagioclase, pyroxene, and that's all kinds of pyroxene, so orthopyroxene and clinopyroxene, and you see olivine. So you have different minerals that you're using to name mafic rocks. And then if it's an ultramafic rock, you're using olivine, and then you distinguish between orthopyroxene and clinopyroxene to name a rock on one of these diagrams. So again, if, for example, a mafic rock, if it's a basalt that, we'll just keep it simple, call it 50% pyroxene and 50% plagioclase, because we know it should be about 50% dark mafic minerals. A basalt composition, that is. I'm using a volcanic term here, but these diagrams only apply to plutonic rocks. But if it's a generic basaltic composition overall with 50% pyroxene, 50% plag, then it's going to plot right around the halfway point between plagioclase and pyroxene. That's assuming it has no olivine in it. And you ignore the fact that if it has any hornblende in it, for example, or any other minerals growing in that gabbro. Okay. I like this diagram because it is a good way for you to visualize the minerals that are common in plutonic rocks, and that you should expect to see more of for any given composition of the plutonic rock that you're looking at. And so what I want you to see is, in particular with it, is that if you're looking, let me explain the diagram first. What this is over on the right-hand side, you see mineral percent. It goes from 0 to 100%. 100's up here, 0 down here. And so you're looking at 100% of the minerals in the rock, and this is breaking it down in proportions of 100%. So if you're looking over here at the felsic end member, you see it looks like it has maybe 40% K-spar, the orthoclase, 30% quartz, 10% sodium-rich plagioclase, so an albite. What are we up to? That's 80%. I kind of underestimated those, didn't I? And then the rest of the rock is made up of biotite and muscovite. So that's how you're kind of reading that part of the diagram. Down here, you've got a volcanic rock name, a plutonic rock name, and then the generic terms felsic, intermediate mafic, ultramafic for what those correspond to. And also you have a scale for the percentage of silica in the rock, how much iron and magnesium might be in the rock, how much sodium and potassium might be in the rock, and the color. So that's how you use it. So you can estimate the color index, you can estimate the chemistry, you can estimate just the sort of general composition, and what minerals you can expect to find in an intermediate rock, for example. So if you're looking at generic intermediate rock, you expect to see some quartz, some plagioclase, some hornblende, some biotite, and maybe a little bit of pyroxene. If you're looking in an ultramafic rock down here, you're looking at a rock that is dominantly olivine and pyroxene, probably doesn't have any plagioclase in it. A mafic rock is going to be comprised of a calcium-rich plagioclase, some amphibole, some pyroxene, and maybe a little bit of olivine. So that's how you're supposed to use this. So it's a nice guide. It helps you remember what minerals you should expect to see, particularly when we're looking at the plutonic rocks. All right. Now, to Bowen's reaction series. I showed you this before when I was telling you about the silicate subclasses. And as far as using this to show an increasing complexity in the crystal structure of the minerals as you move down in temperature, down the discontinuous crystallization series. And again, I use that to explain, okay, we have the simple silicate minerals, the isolated tetrahedra of the olivine crystallizing early in, I use the example of a partial melt of the mantle, so basalt magma. And olivine would crystallize out first, and the pyroxene, then the amphibole, the biotite, and then over here on the continuous crystallization series, the calcium-rich plagioclase first, followed by the sodium-rich plagioclase, down into more case bars, muscovite, and quartz. And these correspond to these terms that we've been talking about with ultramafic, mafic, intermediate, and felsic. So ultramafic rocks, just like that colorful diagram I just showed you in the last slide, ultramafic would be comprised of olivine and pyroxene, and this gives you the idea that it might have calcium-rich plagioclase, but I just explained that's not true. Mafic rocks having maybe some olivine, pyroxene, maybe some amphibole, calcium-rich plagioclases. Intermediate rocks having, intermediate rocks having, some mixture of calcium and sodium-rich plagioclases, pyroxene, amphibole, maybe pyroxene, more amphibole, more biotite. And then the felsic rocks being comprised mostly of the sodium-rich plagioclases, biotite, case bar, muscovite, quartz. And the last couple of things I'll point to on this diagram are these arrows on the right-hand side. And those show you increasing, this first line right here is increasing silica, sodium, aluminum, and potassium. Those are the key chemical components that you expect to see in increasing quantities as you move down Bowen's reaction series. So those elements stay behind in a melt longer than the more mafic minerals. And those more mafic minerals, the arrow on the right-hand side shows an increasing amount of iron, magnesium, calcium as you move up Bowen's reaction series. So there are a couple things going on with the chemistries changing as crystallization of a magma proceeds. And that's an important thing to know because those elements show up in these minerals that are on Bowen's reaction series. So if you were going to estimate a composition of plutonic rock, you could have an idea what minerals you might expect based on how much iron, magnesium, or calcium you expect to find in that rock. All right, what you learned in this module was igneous rocks are classified by chemical composition and texture. You can't consider just one, you must consider both the chemistry and the texture. That plutonic rocks are phaneritic, and that's the only term you're going to use to describe a plutonic rock. Volcanic rocks can be aphanitic or porphyritic. You can generalize about the composition of an igneous rock using the terms felsic, intermediate, mafic, or ultramafic. The color index can be used to approximate the chemistry. There again, just be careful because it's not cut and dried, and especially when we get to volcanic rocks, it's trickier. But I'll explain some tricks you can do to help with that. Plutonic rock names are based on those IUGS diagrams, and only those minerals that show up on the corners of the appropriate IUGS diagram. And that Bowen's reaction series shows the mineralogic and chemistry changes that you expect during the cooling of a magma. Okay. Now please go take the quiz on igneous rock classification, plutonic rocks, and Bowen's reaction series.